Well, so today we are going to talk about a specific kind of problem which we call as constraint satisfaction problem. And life is full of constraints. There are so many conflicts, and of course, during the journey of our life, we have certain goals to meet, and the goals to meet that should satisfy different constraints that come in our way, right? So I'll not tell you that these kind of problems or the approaches that we are going to talk about, they will solve all your real life problems. But I can assure you that some of the problem domains that we will be discussing here, they are really elegantly solved using these kind of approaches. So with this, let us start working on these specific kinds of problems, which we call as constraint satisfaction problem, and it is a subset of or subclass of such problems that we have talked about, right? So this particular slide I'll not like to talk about because I have recorded this video and put this up on the YouTube. I hope you can see it there. So it is basically providing an overview of the things that are related to or different concepts that are related to this constraint satisfaction problem. And of course, we'll not be touching upon all the ideas. Maybe we'll be touching upon some of the ideas from this set, right? So first, in the first phase, we'll try to talk about why do we need CSP and what is basically CSP. So in the first part, I'll try to set the context for the use of the CSPs and the related approaches, and then try to talk about different solvers that are there in this CSP domain. So from now on, I'll not be uttering the entire term constraint satisfaction problem. I'll just say CSP, and by CSP we mean constraint satisfaction problems, right? Now, if we talk about uh, AI problem solvers in general, so let's say before attending this AI course, if I ask you to write some code or a code for a search problem that has have been discussed in the earlier classes. So take an example like say 8 puzzle problem, right? So how would you go about it? So assume that you are not in an AI class, you've just maybe done your first year or maybe second year, but never attended an AI course. So how do you go about it? Anyone? So I'm talking about this block puzzle problem where we have got this 1 to say 15 number. You have to arrange them in this block. So this is the problem that you're given with. And I guess this problem has been discussed earlier.
So, sir,
Hello. Yeah.
specifically talking about this problem, the sliding tiles problem.
Right.
Like
Right.
I would be starting with an initial state, and if I
Mhm.
did not have any idea about AI, so I would simply use a graph search algorithm like BFS or DFS.
Mhm.
And from that initial state, I would go and explore all of the state space that is possible, and I
Mhm.
would define a leaf node where my sliding tile like reaches the goal state.
Mhm.
After I would have like now I would have several solutions, and I would tabulate that what is the net amount of steps to each solution. From there I would compare. This would be like the most rudimentary way without doing any use of artificial intelligence.
Okay, thank you, thank you. So basically, the point that I'm trying to make out here that we would have taken a very brute force approach. So we have a problem to solve. Let us code it. That's how we go about it. But while we were discussing the search algorithms in this AI course, there we understood that, well, these problems have got a very specific structure. So for example, this problem can be mapped in a kind of state space related situation where you have got multiple states. And if you take an action, you go to another state. And in between, what you can do from a state, you apply a successor function to go to the successor state. And at each step, you are just trying to check whether the state that you arrive at, whether that is a goal or not. So basically what we are doing here, we are kind of generalizing our algorithm or implementation, right? So what is the kind of generalization that we have approached? So basically, any given search problem, we can model that in a state space. And basically, you have to implement these two functions like successor function and is goal function. So if we can define that, rest of the structure will more or less remain the same, right? So in a nutshell, what we are achieving a kind of generalization, right? But so what we have achieved, we have got a overall structure of the code which is problem agnostic. So that means it is not dependent on any problem. You can fill in any problem and that will kind of follow this kind of structure. The implementation will follow this structure. But there are two entities that are still domain dependent. First one is the isGoal function and isSuccessor function. So if I give you this sliding tile problem and say water jug problem. So the successor function for this tile problem will be different than the successor function of the water jug problem. And similarly, the goal testing will be also different, right? So though we are claiming that we have come up with a generic structure, but the individual components you have to write in a very problem specific way. So the question is, can we have a truly generic problem solver? So by truly, what do we mean? So let us see what are the implications of this statement. Well, the answer is yes, we can do that, but not for all the problems. So we have a specific class of problem for which we can do that. And this specific class of problem, which we call as constant satisfaction problem. Now let us look at the implication of this question. Like we want to have a truly generic problem solver. So there are two implications. So first one is we need to make this is goal and the successor problem functions to be problem agnostic. So what do we mean by that? So basically we need to write a goal test function which does not depend on the problem that we are addressing, or the successor function should also be problem independent, right? And most importantly, we have to design and methods and the heuristics that are also problem agnostic. Now let us compare these requirements with whatever we done till now using the search algorithm. So this part we understand, right? So this part is problem dependent. Design method, well, some part of it is problem independent because we know that these are the steps that we need to do. But heuristics function, still it was problem dependent in case of search, general search problems, right? So for this sliding tile puzzle, we would have taken, say, Manhattan distance to be our heuristics, right? But for water jug problem, we would have taken a different heuristic, right? So what we are claiming that for these class of problem like constant satisfaction problems, we will come up with these functions like isGoal, successor, and we'll devise methods and heuristics that are problem independent. So this is our claim, and we will try to discuss all these claims as we go forward, right? So basically, if you understand the philosophy of this constant satisfaction problem, so the philosophy lies in this particular statement that we can have truly generic problem solver if we can make this isGoal successor function problem independent, and the entire algorithm or the method that is problem independent, and most importantly, the heuristics function that we'll be using, they should also be problem independent, right? Now let us, to put the thing into perspective, let us try to revisit the search problems, right? So if we look at the problems that we have solved in the search module, so basically we have talked about single agent, though we have talked about game trees where we have got adversarial agent. But let us talk about the problems like 8 tiles and other. So those are single agent problems. So single agent is trying to solve the problem and the actions are deterministic. So for a given state, if you take an action, you arrive at a determined state, right? A state which is unambiguous, right? And of course, your state space is fully observable. You can compute the entire state space, though it might take exponential amount of time, but it is observable. And finally, that states are discrete, right? So it's not like that you are asking the helicopter to turn the, say, uh, mm, handle by, say, 5.5 degree, not like that. So we are talking about the search problems where we have got these characteristics, right? Now we can look at search to be to plan a sequence of action, right? So you can view search as planning a sequence of actions, right? And what is important there? Important there is a path to the goal. So I'm just marking this word path because this will come back while we talk about the other kind of search problems, right? And of course, as you have might have multiple paths and the paths might be having varying costs and they might appear, the goal might appear in different depths, right? And we understand that we have solved several such problems, right? And as the state space can be exploding, we make use of heuristics to prune the search space. So basically, this is what we have done. But the most important thing that I want to highlight is that we are interested in a sequence of actions. So that means a path from the initial state to the goal state. So that is one. And the second one is that path can be of varying length. Of course, if the lengths are varying, they can be of varying costs, and the solution may appear in different depth of the search tree, right? Now, we can also look at a kind of problem which are kind of problem of identifying a goal. So I'm not interested to know how I have arrived at the goal, but I'm interested to know whether goal can be arrived, right? So here the philosophy is that goal is important, but not the path, right? And we'll see later that the characteristics of this kind of problem is that all the paths from the initial state to the goal state, they are at the same depth. We start with some initial state, and as we expand, we reach a state like this, maybe this, or something like this. And so all the solutions, they will be at the same depth, right? And basically, the CSPs are uh, the search problems which are identification type. So here we are interested to know whether we can achieve the goal, but we are not really interested to know the path to the goal, right? So it kind of simplifies the problem a little bit, but it has got utility in many domains. So we'll see in which domain we can apply these kind of CSVs. So let me tell you an analogy in this case. So let's say Sherlock Holmes has been given with an assignment. For example, he has to catch say a thief, or no, so he has to find out something has been stolen, for example a diamond, right? Now for the person who was possessing the diamond, what he will be interested in, so he or she will be interested in to just retrieve this diamond, right? So it is not really important for him or her to understand, in most of the cases of course, how Sherlock Holmes has really arrived at the solution, right? But for the readers like us, or maybe for the inspectors, so they will need to know how Sherlock Holmes has deduced this goal, right? So you can think about this deduction part, like starting from the initial state to finding out the diamond is a kind of general search problem where we are planning a sequence of action. But for the person whose diamond was stolen, for him or her, this identification of the goal is important. So that's how we can think about it, right? So I don't know how many of you have seen this problem. So have you ever seen this problem? Anyone? Shreya? Hello? Hello, are you all there?
Yes, sir.
Yes, sir.
Yes, sir. Yeah.
Yes, sir. So I'm just asking whether you have ever seen this problem,
No,
even
sir.
without description. Well, the idea is, so you have a network which is not configured, right? What you have with you, only a bunch of nodes, and the nodes, they're having a value which is the degree of that particular node. So for example, the degree of this particular node is 2. So that means it can have at most 2 connections, or it will be having exactly 2 connections, right? So I cannot have a connection like this. So either this or this or the other, right? So you see that we are putting our constraints on the number of connections that each node might have. And you have to jointly assign the connections so that the constraints that we are imposing on the connection of the individual nodes, they will be satisfied, right? So as you can see that here again, we are talking about constraints, right? So if we take this problem, now you understood the problem, right? So now if we try to map this to a search problem, so what is the first question we need to ask? So you need to ask what is the initial state, right? So what is the initial state? So the initial state would be, I do not have any connections, right? Only I have the nodes and their degrees, right? So no edges are connected or assigned. Then what is the next question I need to answer? What is the successor function, right? So what is the successor function here? So the successor function is that if we add one edge like this, we have a new network, right? And we know that if we add this, the remaining value here will be 0 and the remaining value here degree will be 1. So this will be our successor state, and we can define this action that we are taking. I'm not going to do that, but you can think about the action that we are taking. We are just connecting two nodes, right? And you have an effect, right? What will be the third question? The third question would be like whether, so third question will be the goal test, right? So whether each node has the number of connections that is equal to the degree value that is associated with each node, right? So that is the kind of goal that we have, right? Now, a pertinent question here is that, is the path to reach the goal is important, or I just want to come up with an assignment or configuration? So we want to come up with an assignment or configuration config that will satisfy the goal condition, right? So this is what we need to do. So if we want to do this, we will frame this problem differently, right? So this is exactly what we'll be doing here, right? So if we look at a standard search problem, so the core of a search problem is the definition of a state. And we know that definition of state is problem dependent, right? And you define an arbitrary data structure for a given problem, right? So as I have mentioned earlier, that for water jug problem, my data structure for the state would be different than for a problem which talks about, say, sliding puzzle problem, right? Now, as we know that the goal test function, so what is the kind of nature of this function? So if we say that G is my goal test function, so what it does, it takes as input one state and outputs either true or false. So this is my goal test function. And the third thing is the successor function. So if we just say f is my successor function, so we have one state and an action. So it is a kind of Cartesian product of the set of states and the set of actions, right? And this will give us a state, right? Now you see that input to each function, this goal test and successor, they are the states. And state is problem dependent. And as state is problem dependent, this goal test and successor function is bound to be problem dependent. Whereas for the constant satisfaction problem, which I have already mentioned that it is a subset of such problems. So we define the state in a very generic way. So how do we define a state? So basically, we define a state to be a collection of variables. So here xi's are my variables, right? Now these individual variables, they can take a value, right? So that means each variable is associated with a domain. So domain is basically a set from which a variable can take a value, right? So if you go back to the problem that we are discussing, this network problem. So what can be the variables? The variables can be the edges that are unassigned, right? So those are the variables. And what can be the domain of each variable? The domain can be either I connect a pair of node or I do not connect. So basically the domain for our case, for that particular problem, will be either we connect or not connect, basically true and false, right? And how do we define the goal test? So basically the goal test function can be defined as satisfaction of a set of constants. So we want to see whether we satisfy a set of constants. And in our example case, what is the set of constants? The constant is that for every node, whatever value we have in that particular node, the degree value we have, we should have exactly that many connections coming out from that, right? And we'll see later that these constraints we can define as a legal combination of values from this subset of variables. So we'll just explore it later, I think 1 or 2 slides down the line. So let me give an example of such problem. So this is, I think, the widely celebrated example of constant satisfaction problem. So you have a map and you have to color the map in such a way that no two neighboring states will be having the same color. And you may be given with a problem like I am giving you 3 color and tell me whether you can come up with a configuration which will satisfy this constraint. And what is the constraint? The constraint is no two states will be having the same color, right? So here you can see that we have one configuration which is a satisfying configuration, right? Now let us try to go it in a bit formal way. So how do we define a CSP problem formally, right? A CSP problem really contains 3 sets, right? So one is the set of variables. So this X is the set of variables. D is the set of domains. And C is the set of constraints. So these are the 3 things that defines a constraint satisfaction problem. Great. Now, while we define a set, so for every element, when we define a set of variable, so for every element in this set of variable, we need to define that domain. So basically, we are saying the domain of xi is di, right? Now, how do we define the goal test function? The goal test function is basically a set of constants like say ci, and each ci is a function of x prime. And what is x prime? X prime is a subset of the variable. So basically, I'm defining the constraints to be a function over a subset of variables, right? Now, for every constraint, we have to define, we have to declare two things. One is the scope of the variable and the relation. So let me tell what is the scope of, sorry, not scope of the variable, the scope of the constraint. So the scope of the constraint says that what is the subset of variable with which I am defining the constraint Ci. So again, I'm repeating. So the scope of a constraint is basically the subset of variables x prime, which I am using to define my constraint, right? And what is the relation? The relation is basically will tell, so I'm talking about relation. Relation will tell how the variables in x prime are related, right? So these are the meaning of these two components of a constraint, right? Now, depending on the situation, this relation can be implicit or it can be explicit. So you'll see some examples of this. So basically, if we say that we have basically two variables, right? So I'm defining my constraints using two variable x1 and x2. So the scope of the constraint is x1, x2. So this is my scope. And what are the relations that I'm talking about? I'm saying that A is related to B and B is also related to A. So basically that is how we are representing the relation, but also we can represent the constraint in a different way. So I'm defining the scope in the similar way. And I'm just saying whatever be the value of x1 and x2, this should not be equal. So these kind of constraints are called implicit constraints, sorry, explicit constraints. So these are explicit constraints and these are implicit constraints, right? Now, after we have defined a CSP problem, let us define what do we mean by solution. So for solution, the first thing that I like to define what we call as an assignment. So basically what we have in the problem, we have got a set of variables and we know that each variable can take a set of values, which are basically the domains of the individual variables. Now the solution is basically is an assignment of the variables with some values, but that assignment should be valid. More or less, that is the kind of definition or informal definition we can have for a solution. So for a formal definition, so let us first define an assignment. So basically assignment is something where we are assigning values to some or all the variables. So if you're assigning values to some variable, so that is a partial assignment. So you are if you are setting the values of some variables, we are calling that as partial assignment. And if you are setting the value of all the variables, that is full assignment. So we will see later that while we are working on the algorithms, so we may start with a partial assignment. Our goal would be to come up with a full assignment finally, right? Now we define something called consistent assignment. Now you can guess what do we mean by consistent assignment. So let's say we are having, say, n variables. So say 10 variables in our problem space, right? Now out of these 10 variables, I have assigned two variables, the values of the two variables. Now I can check whatever values that we have assigned to x1 and x2, say A and B, this assignment is violating any constraint or not. If it violates any constraint, it will be an inconsistent assignment. Otherwise, it will be a consistent assignment. Now, a complete assignment is something where every variable is assigned a value, right? So here we are not leaving any variable unassigned. And finally, the solution is something which is an assignment which is consistent and complete. So that means we have assigned all the variables, but we have not violated any constraint on the run, right? Now, with this, so our claim is that we can come up with general purpose algorithms that will have more efficiency or more implementational flexibility than the standard search algorithm. So that is our claim. And let us see whether we can go forward with that claim. So before I go to solver, so let us try to see how we can map a given problem into a CSP problem, right? So the first problem that we like to talk about is the problem of Sudoku. And I guess you know what Sudoku is. So let us try to find out the variables. So what do you think? What should be the variables? Can any one of you respond to this?
All the cells in the Sudoku map.
All the cells in the Sudoku map. Okay, variables are all the cells. So I'm just not writing the other part. So any other comment from any other person here?
Like essentially empty. I just, yeah.
Essentially empty in the sense? Okay.
Empty cells, the empty cells.
So you need to take the cells that are open or empty, right? So basically, I'll not be taking these as a variable because that is already assigned, right? So our variables are each of this open squares. So what would be the domains? Yeah, I think we can do it together.
1 to 9.
Exactly. It will be 1 to 9. So these are our domain, right? So what would be the constraints? You know it, you just need to spell it out.
That row, column, or the box should not have a number.
Okay, so actually the values that we are assigning in this row or column or any box or any region, this particular region should not be the same, right? So basically, we can linguistically write that as say we are doing all say 9-way all def in column and similar in rows and similar in the regions. So this is what we are defining the constraint in what way? Implicit or explicit?
Implicit.
This is an implicit. So can we make it explicit constraint? Can we try it for say column?
Like we would write like the first element will not be equal to the remaining of the empty boxes and
Exactly.
the second element, so on and so forth.
Good, thank you. So basically, if we name the squares like say A11, we'll say just A11 is not equal to A12, then A11 not equal to A13, and so on and so forth, and then A12 not equal to say A13, something like that, right? So now you can see that given a problem, we can map that to a CSP problem, right? Now, how do we map this problem to a CSP problem? Again, we have to just answer three things. First one is the variables. Variables would be what? Basically the states. The states are individual variables. So basically we can say that WA is a variable, North Territory is a variable, South Australia is a variable, Queensland is a variable, New South Wales, Victoria, and Tasmania. So these are our variables. Domain would be basically 3 colors. So we are asking whether we can color this with 3 colors. You can pick up any 3. So you're just choosing blue, red, and green. And so this problem will be using to illustrate whatever things we'll be doing later, most of the cases. What would be the constraint? The constraint would be very simple, that the adjacent regions, they should have different colors, right? And can you tell me what should be like implicit constraint? So how do we define an implicit constraint here?
Like Western Australia should not have same as Northern Territory, and Western
Exactly.
Australia should not have a South
And
Australia.
yeah, we can go on writing like this, right? And what can be an example of, say, explicit constraint?
Like we can take a tuple of, let's say, two neighboring states, Western Australia and Northern Territory, and
Okay,
then we define the all possible values of tuple such that both
okay,
the entries don't have the same color. So like red,
okay,
blue, red, green.
okay, great, great. So can we say something like this? So red, blue, red, green, and so on and so forth. Is it fine? So basically all the allowed combination for adjacent thing, right? So this is how we can map this map coloring problem to a CSP problem, right? Now, again, we'll be talking about another celebrated example of CSP, which is what we call as n queens problem. And you know the problem. You have to place, say, 8 queens on the chessboard so that each row and each column will be having one queen, and no two queen will be attacking each other, right? So there can be multiple formulations. So I'll be illustrating 2 formulations here. So the first formulation assumes. So how do we go about it? What can be the variables? What do you think? Is very important. Unless you can map a problem to this kind of formulation, you cannot really see whether I can use solvers, CSV solvers to solve this. So can I say that this individual cell is a variable? And so what I'm trying to mean that this xij, where I and j is basically 1 to say n, right? Each of the cell is a variable. And what are the values? So either there is a queen in that cell or there is no queen in that cell, right? How do we define the constraints? Any idea? If we have this kind of variable and domain structure.
Sir, any Xij should not be attacked by already placed queen.
Any xij, can you repeat?
Should not be attacked means should not be come in the area of
Yeah.
previously placed.
Okay, so you are specifying a very high level constraint. So how do we really put that to a grounded manner so that that can be implemented readily? So I have just these variables. You have to define anything using whatever you think using a variable. So Can we go a bit granular way? Can we define the constant using these values?
Summation j from j equals 1 to 8 equals 1.
Hello, can you repeat, please? Your voice is breaking.
Summation x1j from j equals 1 to 8 equals 1. Same.
Sorry. Sorry, I could not. Okay, so let me guide you through. Maybe you have got the right solution, but I could not hear you properly. So let's.
Some the for like some of these cells, like there should be only one queen in each row and each column. So summation of the xi's and xj's, we can say it is 1.
So it will be 1 and summation I xij should be 1. So is it something like you want to say?
Yes, sir.
But with this, can you make sure that the queens will not be attacking? So check it out. So I'll just ask you to check it out whether this will work. So I can give many examples where this will not work. So I just.
So we have to consider the diagonal shots as well.
Yeah, diagonal is also important. So we have got three kind of things we need to take into account, right? Yeah. So this is a kind of clue that we have got. So let us try to see. So let us try to address the diagonal part first, right? So let us, what is this? This is x11 and this is x122, right? So if we have, so let us try to make it explicit, try to have explicit constraint here. So x11 and x22. So this is a tuple, and this is where we are defining what? The scope of the constraint, right? And what are the kind of relations that are allowed? So if I do not have any queen in this or this, there is no attack, right? We do not have a queen on x11 and we have a queen on x22. That is also satisfying our constraint. And finally, I have a queen on x11. I do not have a queen on x12. So I think this is it. I cannot have this combination. This is not allowed, right? So with this, let us try to formalize it a little bit. So we'll do it for the columns, for the diagonals, rows and columns, right? So basically, I have got, say, ijk, I have got xij, and xik. So that means we are addressing the cells that are on the same row. We are addressing the row. And what are the allowed values? The allowed values, either they do not have queens both, and one of them is having the queen but the other not, right? So this is how I have addressed row. How do I address the column? The reverse way, right? So basically I can say x ij and x, say, kj. And this should belong to the same set, right? And we can have ijk, xij. Now I can add k to I and k to j. So that will give us a diagonal, say, upward, right? So ik, ik and x j plus k. This should belong to the same set. And finally, for our all ijk, the other way, right? I minus k and j minus k. this should belong to this same set. So this is one way by which we can formulate this n queen in a CSP. So there is another formulation which I think I'll be skipping for now. You can look at the video and check what is the other formulation, right? But just to give an hint, here we can take the individual queen to be a variable. So that means if we have 8 queens problem, we have got 8 variables here, and we need to define the uh, mm, constant using those variables. So I'm not going to do this. So you can maybe have a look at the video, or you can try it out yourself. Right. Now, with this, let us talk about some of the applications that CSP has, real world applications. I'm not talking about toy problems. The first problem that I'd like to talk about is the application in Hubble Space Telescope. And this was a kind of widely celebrated application of CSP. So the problem goes like this. Hubble Space Telescope makes around 30,000 observations per year. And there are many constraints. For example, uh, mm, the observation or the kind of movement that or kind of, so basically one got to schedule this 30,000 observation over the period of 1 year, right? And how, on what parameters these observations depend on. So one parameter may be in which location of the orbit this Hubble Space Telescope is situated in. That can be one parameter. There may be parameter like I'm trying to observe one interstellar body which may be located in different angular or different positional location, which is also kind of constant because let's say you are looking at one part of the sky and I ask you to do an observation within say 5 seconds to say completely a different part of the sky. That might be very difficult for Hubble Space Telescope. So you need to really schedule that. Or while I'm moving the apparatus of the telescope, there are power. So amount of power that requires to move the uh, mm, elements that might vary. So you want to optimize that as well. And finally, the scientists, they can have their own priorities. And with all these, you have to come up with the schedule for the entire 1 year, right? And that was successfully done in NASA AI laboratory using this constant satisfaction problem. Of course, they use some sophisticated heuristics to do that. Some of the heuristics we can talk about later. You think about an airport where you have got multiple airplanes arriving, departing for different airlines, and different airlines, they have got different priorities, and there might be delays, and there are many things. Scheduling the airlines is very complicated. That depends on many parameters like weather, availability of the pilots, and there are many things, right? And you need to come up with a schedule that will not clash with any other things, because a very minor mistake can play havoc here. And constant satisfaction problem solvers, they have been widely used to come up with very non-conflicting solution for this airline scheduling. We'll talk about a problem which we call a script arithmetic problem, which can give you a glimpse of how this can be used in cryptographic applications. If you think about projects, they involve many human and non-human resources. There are many stringent goals and many other things. There are so many constraints involved in project that involves a big team. And coming up with a plan is really challenging, and CSP has been widely used there. And finally, I can talk about the timetabling problem, where you have, say you think about a department where you have got many professors, many students, and there are many courses that are being offered in that department. And there might be preferences of the professors and preferences of the students, and there are so many things. I need to combine all these things to come up with a timetable that will not conflict anyone's interest, either for the students or either or not for the faculty members, right? So these are some example applications, but I'm sure there are many other applications out there in different other domains. And I was talking about addressing your queries today on your assignment and video topic presentation. So I think you can explore a little bit to check what are the applications that CSP has got in your domain, right? So how much time we have got today? So a little bit of time. So before going to the solver, so let me give you a kind of glimpse of a kind of generic structure of the problems that we'll be using to solve the problems like CSP, right? So let us try to convert this map coloring problem to a very famously known problem, and it was solved. It remained unsolved for more than 100 years, and that is called a graph coloring problem. So what is the graph coloring problem? So graph coloring problem is something like this. So you have a graph which is a planar graph. So planar graph means you can draw the graph on a 2D plane without crossing the edges, right? So if you have that kind of graph can be colored with 4 or less colors. So that was proposed by Guthrie in uh, this was a hypothesis, and back in 1852, and it remained unsolved for at least 120 years, and finally in 1977 it was solved. So I am bringing this out here because we'll see that we'll map these problems into graphs, and then we'll just forget about the problem. What was the problem? We'll just forget about. We'll try to analyze the graph and come up with our solutions. So let us see what we're trying to do. So basically, we are talking about graph as an abstraction tool. So let us see. This is a kind of problem that we are with, and we have these variables, right? And we know that these variables, they interact through constraints. So what are the kind of variables, constraints we are talking about? Like WA and NT, they should not be colored with the same color. And you can see that you can connect these nodes or variables with these constraints and each edge is signifying a constraint, right? And if we have that kind of structure is called a constraint graph, right? And if you have a binary CSP, and basically a binary CSP is a CSP where your constraints involve at most 2 variables. So here the constraints involve at most 2 variables, right? And if you have a constraint graph for this binary CSP, that is called a binary constraint graph. And you can see that this binary constraint graph can be represented as a graph where the nodes can be variables and arcs can be the constraints, right? So basically the claim is the CSP algorithm will leverage this graph structure to speed up our search. So we could have solved this using search problem, but we are going to a specific class of problems which will just look at this graph kind of structure where the individual nodes are the variables and the connections are really the constraints, right? So this is the kind of graph that we'll be talking about in the future classes. And well, so I think let me stop here. If you have any doubts or questions, whatever we have talked about in this class, I'll be more than happy to answer. I think, yeah, I'm done for today. So any questions, any doubts on this till now? Okay, great. Thank you. See you tomorrow. Thank you very much.